Welcome to Kitchen Table Electronics Module 5. We're starting to learn about AC circuits, that is alternating current, and components that react to alternating current, presenting a resistance or reactance. And to play with these components, we're going to want to be able to alter the frequency of the alternating current that passes through them. To do that, we would love to have a signal generator, but they're expensive. And since the whole idea of this course is to teach you how to automate your measurements with a microprocessor, we'd like a programmable signal generator, but they're even more expensive. And so we are going to start by making our own programmable signal generator. So, welcome to the world of direct digital synthesis, DDS. Why do we need to get so seemingly complicated? Well, we can use the Arduino to generate changing voltages that change with time, but as you saw, we could only change them very slowly. This was because of the pulse width modulation used to generate an analog output, and we had to use a long time constant to smooth out the variations from the pulse width modulation. However, as I hope you have learnt by now in this class, you can type into Google signal generator, cheap enough for an impoverished student to buy, works into megahertz range, is programmable, and hit enter, and up will come, amongst other things, the AD9850 chip from Analog Devices. So once again, in this day and age of electronics, you can't possibly learn everything that's out there, but Google will help you find precisely the chip you need, and this is it. Luckily, it's such a popular chip that many people sell working boards with the chip mounted on it, and all the auxiliary electronics, which includes the clock that the chip operates on. You can get this very cheaply. I went to Newegg and I waited actually 2 months for delivery, or you can get it on Amazon Prime for about $22. What direct digital synthesis does is to generate a streams of 1 and 0 at a frequency of the clock, which is 125 megahertz in this case, a very high frequency. You get the final output by dividing the clock frequency by a number that can be as large as 2 to the power 32, 32-bit number. So the smallest change in frequency you can make is then 125 megahertz divided by 2 to the power 32, and of course you divide by some other number less than that for some other frequency. Of course, the output is now still a stream of 5 volts and 0 volts, or ones and zeros, but on this chip it's converted to something that looks quite a bit like a sine wave by an analog to digital converter that consists of a series of diodes and resistors. So here is the first part of the data sheet. You'll find the data sheet in the resources folder on the web page. This is for the chip alone, but I always urge you to read the data sheet. A lot of it won't make any sense, and that's fine. But as you read more and more data sheets, you'll learn what to look for. And then when things don't work, you'll also learn how to search through the data sheet and find out maybe what mistake you might have made, or where there's a limitation of the chip. So this clock in here is the 125 megahertz that I was talking about. This is the thing that divides by a number up to 2 to the power 32. It actually consists of something called shift registers. These are pairs of transistors that can store a binary 1 or a binary 0. And if you shift them to the right by 1 bit, it's equivalent to dividing by 2. And so you divide by some arbitrary number with an appropriate number of shifts to the right. The output of these then goes to this digital to analog converter, and here is the analog output. This data register here is where you store the number that does the programming of the frequency. So this is the number that can be up to 2 to the power 32, actually minus 1 because 1 bit is a sine bit. And there are two ways of loading this. The parallel way, which is the very fast changes in frequency, and that's a lot of hard work. We're not going to do that. But the serial load, by sending a set of preparatory pulses along here, you can get this thing to be ready to accept data, and you will actually soon see the resets, the frequency update, clock load, and data pins being used to do exactly this. Just a word of caution, of course, the pins on the chip data sheet have nothing to do with the pins on the board you're going to order. So here in this sort of initial description, the clock rate, the 32-bit tuning word, and then you see it'll handle either a 3.3 or 5 volt single supply, so absolutely perfect for powering from our Arduino. Hooray! Okay. As I said, we're going to use the serial port to program our chip. The data sheet tells us what I just said, which is that the output frequency is some number, which can be up to 2 to the power 32, times the clock input frequency, 125 megahertz, divided by 2 to the 32. So 2 to the 32 herein would just give you the clock frequency, except the chip won't work that fast, so don't try it. This is the number then that we have to calculate, and we do this, we'll multiply f out by 2 to the 32, divide by the clock frequency, and that will give us then the number we have to calculate for a given frequency output. Okay. As I said before, 32-bit binary numbers, 1 bit less than 2 to the power 32. So here is 2 to the 32 minus 1. Check it on your calculator. 125 megahertz. I hope there's 6 zeros here. Multiply by the desired frequency out. And this is the number that we are going to have to pass to that data register to program the chip. Okay. Now let's get down to the details of how we do it with all those various programming pins on the chip. Here's the information on how to do this from the data sheet. It's a little terse, so let me step you through an exact sequence of events that you need to carry out to set this chip up when it's connected to the power supply to be an oscillator on the desired frequency. The first thing you do is pulse that reset pin. And by pulse, I mean hold it at 5 volts for some time and then let it go down to 0 again. And so that resets all the contents of the registers. That W clock pin sets the serial data port, in fact, all the data ports up to say, I am about to get data. The frequency update pin enables the serial mode. So you've now set the chip up to take data through its data pin. So the program will calculate this 32-bit binary number up to 32 bits. Well, we'll send all 32 bits, but most of them might be zeros. We then pulse the data pin with each of these, and we send a clock pulse in between to say you've just got a bit of data. So, of course, if they have a string of zeros, they're going to rely on a clock pulse saying, nothing, clock pulse, nothing, clock pulse, nothing, clock pulse. So there's actually a clock pulse that comes in between this. When we've sent our 32 bits, we then send a null byte, which is 8 zeros, and this tells the chip that you're done programming it. And if you then pulse the frequency update pin again, you will then send the chip into a burst of beautiful oscillation. All right. End of the theory for the time being. Let's turn to how you do this. This is what your board is going to look like. It may look a different color. My board had the pins labeled on the underside, which is just a little awkward. I took a picture with my phone and then very carefully drew out what it would look like when I flip the board over. I suggest you be at least as careful. This is the 125 megahertz oscillator here. Here is the AD9850 chip. And then the this pot here on my chip does nothing. These are the parallel programming import pins here. And then these are the power supply pins here. You'll see that we've got 2 of them, and we also have 2 grounds. The reason for this is that the digital and analog parts of the supply are separated for very good noise performance. We're not going to bother about that because we don't need to separate them. We don't want to have two separate power supplies. So we're just going to jumper this ground to this ground and take it to ground on the Arduino, this 5 volts to this 5 volts, and take it to 5 volts on the Arduino. Once again, let me repeat my mantra. Take your meter and make sure there is not a short between here and here before you connect to your Arduino. Likewise with all of these lines, make sure that none of them is shorted to ground, or you'll wreck your Arduino, or you could wreck this chip. So do go slowly and check everything multiple times. I have simply chosen completely arbitrarily to use the digital output pins 8, 9, 10, and 11 to connect to this clock, frequency update, data, and reset on the AD9850, and then of course the 5 volts and ground on the Arduino to 5 volts and ground on the chip. This is what it looks like. So here is a jumper lead jumping my 5 volts from one side of the board to the other. Here is a 5 volt lead going to the Arduino. Here is a jumper lead putting the two grounds together, and here is a lead going to the ground on the Arduino. And then here are the 4 serial input pins. This is the jumper 5 volt lead here. What I have done is to push the AD9850 board into a breadboard. It's a little tough to do this. My pins were not exactly a 1/10 inch spacing, so be very careful when you do this. Once it's done, I suggest you just leave this board as the AD9850 board and don't take it in and out, because then you can just use these connectors here that you have to connect easily and change connections to the board. So I am showing here this first black lead, which is the W clock lead. That goes to Arduino pin 8. The next blue lead here goes to Arduino pin 9, and that is the frequency update. The second blue lead goes to Arduino pin 10, and I'm going to be using that for data. And then the reset goes, the orange lead here, to Arduino pin 11. All right, so if you want to, you can just upload this Python code from the website. If you're using the Wix website, I can only upload Word files, so you'll have to cut all of the text from the Word file, paste it into Notepad, and then save it as a text file on your computer, and then cut from Notepad and paste into idle. If you do a direct paste from Word into idle, you will have a problem because of hidden characters in the Word interface. So you want to make sure you have text when you paste it into idle. Once you've pasted it into idle, of course, you can save it as a .py file. So hopefully you will save AD9850 Test.doc as it is on the website, and then text as it will come from Notepad into AD9850 Test.py from idle. And here it is loaded up into idle. I'm just going to go through the easy bits to begin with. So this is the usual setup code. Of course, I'm using PyFirmata. I need to import the Arduino toolkit. So the PyFirmata knows what it's talking to. These are the input and output functions from PyFirmata. NumPy is numerical Python, and I need that because I am going to be doing some binary arithmetic that is supported by NumPy. NumPy does just about everything. So you almost might want to import that into programs regardless of what they contain. And then time, I'm importing sleep so I can pause the program for a little while. The usual setup for this particular run, my port was COM3. It will change from computer to computer and time to time that you set up your USB connections. So make sure you have this as the COM port you found using your Arduino IDE or the device manager. This is a PyFirmata instruction that sets up communication, serial communication with the board. The sleep is just to give it time to talk to the board and set everything up. And then if it gets to this print statement, you know all is good. If for some reason you've chosen the wrong COM port, it won't get to this print statement and you'll get an error message. This is just constants. I am defining the pin numbers here, so every time I refer to W clock, the program knows that that means number 8, and so on. So these are those 4 pins defined here. And now I go to tell the board that I want digital output, and I want it from pins 8, 9, 10, and 11. And these are PyFirmata instructions. Once again, you have the PyFirmata reference in the resources folder on the web page. And then I have a variable that I'm calling state, and I've set it to a logic false or a logic true. The reason for doing this is that we need to talk to the Arduino in a binary 5 volts or 0 volts. It doesn't understand ones and zeros, so we will then just need to send it true and falses. At this point, I am just going to put my hands over my ears and say la 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 la. We'll talk about this later. And here's the main program. So we input the frequency we want. We make sure it's not an X, because X lets us quit from this loop. This freakset function does everything we need. And we will go through that later, but it takes the characters from the keyboard and converts them into binary numbers sent to the Arduino. That's all in that subroutine. And then we ask again until we get out of this loop by putting an X. When we do this, we pulse the reset pin high to turn the chip off, and then we exit the board. All right, so without knowing how the code works, you can load it up. Hopefully it'll just run nicely in your idle environment. Of course, you'll need your Arduino connected, and you'll need to have wired up your AD9850. Hopefully all the leads are correct and the power light came on your AD9850. I've connected the channel 1 scope probe to one of the 2 sine outputs. Either one will do. I'm saying sine 1 here. I think later on I use sine 2. I put 1 and 6 zeros into my Python code. I want 1 megahertz, and I hit return, and then kaboom! This is what I saw on my beautiful little Owon oscilloscope. So to see this, you see I've set the time base to 500 nanoseconds per division. I'm going to want you to play with your scope and remind yourself of how to set the time base. I have channel 1 DC coupled, and of course this is a digital chip, so it's going between +5 and 0 volts. The output of the DAC is less than that, but here it is. It doesn't go negative of 0 volts. This is the 0 volt marker on your scope. You can move this trace and the position of 0 volts around on your screen simply by clicking with your mouse on this and moving it around. You will notice that depending on whether you're DC or AC coupled, that this trace may jitter around on the screen. So you can practice triggering by going in here, choosing the trigger function, and setting the trigger voltage so it passes through the sine wave, so you get a nice stationary picture like this. This frequency counter only works if you've got several cycles across the screen, so you will need the time base set up to give you a nice display for this to work. Here is the peak voltage. It doesn't mean very much because we're going up above 0 all the time. Here is the peak-to-peak voltage. That does mean something. That won't change depending on where this average voltage is. Okay. Let me say a little bit about sine waves. Here is a sine plotted out as a function of its argument in degrees. So if we're looking at time, which we are on the oscilloscope, remember that the degrees in the argument of a sine function change as omega t. So omega is 2 pi times the frequency in hertz. And so when the product of f and t is 1, the sine has gone from 0 to 2 pi, and that is 360 degrees, just to remind you. So here it is plotted out as degrees. Here's 0, here's 2 pi or 360. Here's 180 where the sine changes direction. So this is the familiar sine wave. The average of a sine wave is 0, of course, if you are AC coupled, and we'll look at that in just a minute, so that this point starts at 0 as a sine really would. We're not adding a constant to it. So the average voltage is 0. How do you characterize then the power carried by a sine wave? Certainly not through the average voltage. You do that through the root mean square voltage. The reason you do that is the power delivered is proportional to the voltage squared divided by the resistance of the load. So you need to square this and then average it, and you'll find that done in the advanced topics section on this module. And when you do that, you find it's the peak voltage divided by √2. So 0.707 times the peak voltage is the RMS voltage. And that's also displayed on your oscilloscope. So now what I've done is I've gone down to this channel 1 box here, clicked on it, and I have changed the DC here to AC. So now the probe is AC coupled, and you'll see now that 0 volts is along here, and this waveform is going positive and negative of 0 volts. Okay, so how well does your chip work? The data sheet says that the chip can go as high as the clock frequency divided by 2, and technically that is right. But you will see the output falling quite dramatically. So start at 100 Hertz and then choose to jump up in some multiplicative step, because you're going to put this on a log plot to cover the huge range of frequencies you're going to observe. Take a look at the output peak-to-peak voltage. Remember, measure the peak-to-peak voltage in the AC coupled mode and not just the peak voltage, because if you're DC coupled, that's kind of arbitrary. So measure the peak-to-peak voltage. It's a function of frequency. Start at about 100 Hertz and go as high as you can go and still see a signal. All right, that's your homework. Now I'm assuming you've done that, because now I am going to hurt your brains by talking about the binary programming in Python. And this is going to require a little bit of thought. So I'm going to go through it quite fast, but I expect you to go through step by step and prove this to yourselves. Remember, you can always do this in the Python interpreter a line at a time by setting up the appropriate variables. So this is the pulse high subroutine, and pin is the variable because we're letting pulse high be sent to all of those 4 pins. And so it's a write a true followed by write a false. And so since this variable starts out as false, it's a low, high, low pulse, and that is the definition of pulse high. That's easy. Byte transfer. So this is the part of this is the function that takes a byte of data. We've got 32 bits, which is 4 bytes. 4 times 8 is 32. So this transfers 1 byte at a time. And so let's see how it does it. So the argument in here is 1 byte of the 32 bits, and we are going to be seeing how we transfer the bytes in the next slide. Here's a variable I'm calling state, and I'm setting it equal to false. So this is 0 volts on the output pin of the Arduino. Now here is a trick. X is, at this point, a 32-bit integer variable. And you'll see how that is generated later on. So I take X and I AND it with 1. Now 1 in binary is all zeros with the least significant bit being set to 1. So I take the full byte here, I AND the least significant bit with a 1, and if indeed it is equal to 1, then state is set equal to true. However, if it is not equal to 1, then state is left equal to false. What have I done? I've translated the 1 or 0 value of the least significant bit into true or false. And then I do board.digitalWrite, data was the data pin number, I think it was pin 10, .write state, so it's going to send a true or a false depending on what the value of this bit is. Now we have to send the other bits. Before we do that, we have to pulse this clock high, W clock, data clock, to tell it that we finished sending it this bit of data. Remember, if there's a string of zeros and you didn't have a clock pulse managing this, the poor old chip wouldn't know how to count them. So we pulse high this clock pin. So now we're ready for the next bit of serial data. That is 7 bits in all. So we have a little for loop here going between 0 and 7. Remember, the range statement ends at 6 in this case. So that's the next 7 bits. And once again, we set state to false. Now here's a beautiful trick. We take this 32-bit integer number. This double chevron means shift the bits 1 bit to the right. We do that, and then we repeat this operation again. So now we've taken the second least significant bit, we've put it in the position of the least significant bit, we AND it with 1. If it equals 1, then this second bit was 1 and the state is true. Otherwise it stays false. We write again and we pulse the clock, and in that way we write the 8 bits of this byte into the AD9850. Very clever, and these logical operations seem very sophisticated, but actually they are the most basic thing your machine does. So they're actually very, very simple at the machine level. Now, that byte transfer is a function called here by this other function, freqset. So freqchar was the character that came in from your keyboard with the frequency. And so this is a subroutine we called to make the chip work. So first of all, we have to convert this ASCII character from the keyboard into a float. Then we go through this series of pulses. We pulse the reset, we pulse the clock, we pulse the frequency update. Now we do the calculation of that delta phase number that we need to send to the chip in order to get it to give the desired frequency output. And here's a big trick. This is a float, so it's 32 or 64 bits depending on how your machine is set up. We want it to be a 32-bit binary number. This is where numpy comes in. Numpy.int32 returns from a float an integer 32-bit number. So now we have our number that needs to be pulsed to the chip turned into a 32-bit number. Then we call byte transfer, and look at this trick here. This is a 32-bit number. We are ANDing it with 255. 255 is simply 8 ones. So the least significant byte of this is now ANDed with 8 ones. At every position there is a 1 in the least significant byte. There will be a 1 in the output. At every position there is a 0. This AND will produce a 0. So we copy the least significant byte of this number into this argument here, and then we call byte transfer. So we transfer it. Now we go through the same loop again that we used in byte transfer to transfer individual bits, but we use it to transfer bytes. So we've got the remaining 3 bytes to transfer. Remember again, the range statements go 0, 1, 2, and then stops. So now what we do is we take this 32-bit number, we shift it to the right 8 bits, not 1 bit now, but 8 bits. So now we have the second byte in this number. We call byte transfer again. We go around this loop till all 4, we transferred 1 byte here, the next 3 here, and we are done. So finally, we byte transfer of 0. This just sends the null byte through bit transfer to the through byte transfer rather, to the AD9850. We pulse high, and kaboom, we're there. I put sleep for 10 seconds, which is actually ridiculous, but wanted everything to settle down before we looked at the frequency, and you'll see that reduced in later code. So, you've done it. You have a programmable signal generator. You understand how it works in Python code, and I hope I've been doing this for years, but I must say I got a big thrill when I got it working, and I sat at my keyboard and put in all sorts of frequencies and had fun. Hopefully you're going to do your homework and have a plot of output peak-to-peak voltage versus frequency, and we're going to plot that later on. Anyway, we need to build a bit of quite complicated hardware. We could take our AC measurements by connecting our scope to the components we want to examine and driving them with our AD9850. That is not the kitchen table electronics way. We are going to automate our experiments and spend our time having fun writing code and programming Arduinos, not giving calluses on our fingers as we write down thousands of numbers in a logbook. We are going to be so 21st century. So, ready for the next lesson.